Just let me know when you start.
Yes, sir. Yes, sir, you are live.
Well, good afternoon, everybody. We move on to the next lecture in the course of high pressure physics. And we are covering now in this short set of 5-6 lectures, basic principles of shockwave physics. Just let me recapitulate a few points that we covered in last lecture. That a shock wave is basically a large amplitude mechanical wave which is supersonic. And if you launch a large amplitude wave in a material, and if the material has a PV curve which is concave upwards, then that wave shocks up. It's basically because at higher amplitude and higher pressure, the speed of the wave is faster than at lower pressure. And then we also discussed why is shock wave called a uniaxial strain state and how it emerges out of inertial confinement. We also discussed a bit about that, like a large amplitude wave launched into a material shocks up to form a shock wave. A Rees wave, to the contrary, spreads out for the same set of arguments that we used to show that a large amplitude wave shocks up. So now we will proceed beyond it to get insight of how to deduce certain useful properties of the materials under shock waves. Then shock wave is, any large amplitude wave is launched into a material. In principle, one can use material model along with the numerical simulations for analyzing experimental data. However, this becomes a very complex problem because if they change shape as they propagate, then the material model has to be quite flexible and complex, and it may become computationally prohibitive to really calculate all the things which are observable. So what is typically done is, therefore, one launches a large amplitude compressive wave which propagates without change of shape, that it retains its shape. The wavefront is either a discontinuity or a steady wave with a finite thickness. We discussed last time that thickness is basically decided by the competition between the non-linearities of the material and diffusive interactions such as heat flow or effect generation and so on. Now, in this lecture, we will discuss how the various let me just get it pointers in the proper shape. In this lecture, we will discuss how the states which are under shock are related to the states which are ahead of the shock material that is yet not shocked. So incidentally, some of the arguments that I will be giving in coming 2-3 slides are based on the article by George Duval and Pauls in High Pressure Physics and Chemistry 1963. I've given the reference up there. So for a steady wave with a discontinuity like this, that a material which is unshocked in a state which has pressure P naught, volume V naught, it has particle velocity U naught and energy, internal energy or energy content, which is E naught. And once the material gets shocked, that's when it goes past this continuous jump, then the material adopts a state which has pressure P1, volume V1, energy E1, and its overall velocity is U1. So this is, you can view it as a kind of a snapshot of a material being subjected to a material, to a shock wave. So in general, what I'm saying is the subscript 0 represents unshocked, and subscript 1 is representing the shock state. And the speed of the shock wave, or the velocity of the shock wave that traverses, is indicated by d. D is a shock velocity in the laboratory frame of reference. In general, the shock velocity is defined with respect to the material ahead of it. So it's a velocity with respect to this. If this material is at rest, then this d represents the same thing what is being measured in the laboratory frame of reference. However, there could be situations we will discuss where this may not be so, and so one has to be careful about this. So we would derive certain relationships between this state and this state, assuming that a shock wave is a steady state representing a almost discontinuous jump, or a steady jump, whichever is relevant. So here is a set of arguments. Look at a cross section LMNO, and suppose normal to this we are looking into unit area that's along this direction, which we call x direction. We are looking a shear shock wave propagating across a unit area. So then you see a shock wave is at this particular place at time t naught, and within time delta t, it moves on to this particular position. So within time delta t, it has moved a distance, shock wave speed or velocity, into delta t. So this much of material is now really come under shock wave. So, so during the time delta t, the amount of unshocked material, earlier it was having the density rho naught. The material which was under with the density rho naught has now come in here. So the material which is covered by a shock wave in a period of period between t naught and t naught plus delta t is d rho naught delta t. So this much of material, unshocked material across a unit area has moved into the shock state. So its mass is really d rho naught delta t, and the mass which has come in the shock state is because the mass has also, because it has a finite velocity, it has moved somewhat, so it is really now compressed into this particular area or volume. So that is d minus u, and it has now the density rho1, and within the delta t, it is. So the mass conservation implies d rho naught delta t is equal to d minus u1 into rho1 delta t. So you can cancel delta t. So that gives d rho naught is equal to d minus u1 rho1. So one can put it in this form. That is rho1 divided by rho naught is equal to d divided by d minus u. Incidentally, the rho is a density in a general sense, but one can define it as a specific density. So it will be inverse of volume. Okay. So if you put this way, it'll, if you put in the form of the volume, it'll become V naught by V1 is equal to D divided by D minus U1. Now the same argument similar argument can be used for momentum. Remember this picture. I can't show it on all the slides. So the change in the momentum across the surface is really force into distance, force into time, because dp dt dp dt is the force. So momentum, change in momentum is force times delta t. And the force per unit area on the left-hand side, that is here, is difference between the pressure, okay, P1 minus P0. So the change in momentum will be P1 minus P0 into delta T. Now, as we discussed earlier, the mass rho naught d delta T has gained a velocity which is u1 minus u0. So it is u0 here. Okay, if it is at rest, u0 is 0. So, and now it has gained the velocity u1. So it has gained velocity u1 minus u0, implying a momentum change which is equal to rho naught d minus u1 minus u0 into delta t. So we can make them equal by due to momentum conservation, and that implies that p1 minus p0 is equal to rho naught d into u1 minus u0. And in case the initial unshocked material was having zero pressure and its initial velocity was zero, then this particular relation can be cast in a very simple form that P1 is equal to rho naught d u. Similar manner, we can invoke energy conservation. Work done by the external force is the energy change, which appears in the form of change in kinetic energy and change in internal energy. So now we can see the work done is force into distance. Force into distance, sorry, this should happen u1 times delta t. So the force into distance is p1 minus p0 into u1 dt. And change in the kinetic energy is because the kinetic energy has now been gained by a material I showed earlier. This much of material has gone under shock. So this has gained the speed u1. So it is rho naught d delta t u1 square. Half of that is the kinetic energy it has gained. And change in the internal energy would be represented, if E we represent as energy per unit mass, then E1 minus E naught into rho naught d delta t is the change in the internal energy. So energy conservation would give P1 minus P0 into this term U1 delta T is equal to kinetic energy term plus internal energy term. So for P naught is equal to 0, one gets P1 is equal to half rho naught du1 plus P1 minus P0 rho naught d by u. So in a simple form, if you put P is equal to 1 by rho and also use previous two equations, one can write down P1 minus P0 is equal to 1 into P0 minus. So we obtained the three equations. Because they were the first time, these were the people, Rankin and Bouguereau, who derived these equations for the first time. So these are named after them. And three jump conditions represent mass conservation, first one, momentum conservation, the second one, and energy conservation. This would also give you an idea why it is often said that the Shockwave experiments give the primary calibration of pressure. Unlike the static pressure, which we discussed several other talks, which require certain other measurable or identifiable parameters such as phase transitions and so on and so forth. But in case of Shockwave, because the states before the shock and the states post-shock, they are related to conservation laws of mass, momentum, and energy. Therefore, they do not require anything else to determine the pressure. So this is also called that the shock wave provides as a primary calibration of the pressure. So that's an additional factor that we must remember. That's why the shock wave experiments are done, and we will see probably coming a lecture or two how some of those values are obtained in shock experiments. Now, these three equations obtained by conservation laws are, if you see, it has five variables. It has d, which is shock velocity. It has density. These are unknown variables, d, rho 1, then p1, and e1. So you have five variables in these three, and three equations. So that means for one to determine the shock state unambiguously, we have to know at least two parameters independent, because otherwise these become indeterminate. So two parameters need to be known, and then one can determine uniquely. Historically, the two parameters which were measured in 50s and 60s were shock velocity, that's d, and the particle velocity, which is u1. So therefore, there's a large amount of experiments which have collected the data on all materials in a variety of conditions too, which gives tables of D and U1. These are called Los Alamos compendiums. Huge number of materials, one can get that information. Let me restate again that the jump conditions mentioned, these jump conditions, assume discontinuous steady wave propagation. If the wave is not steady, that it changes shape as it progresses, or it is not discontinuous, then these conditions cannot. For example, if it is a ramp wave, we discussed in the last lecture, a ramp wave spreads out. So it changes shape and it doesn't have a discontinuity. So these jump conditions in principle cannot be used. Another comment, I mentioned that the D is actually a shock velocity in laboratory framework. In general, I mentioned that the shock velocity is defined with respect to the material ahead of the discontinuous jump. If a material ahead is in motion, it also has some velocity, then the term B is usually replaced by what one calls as US. So just to make you familiar of that, when you look into the literature of shockwave physics, you will see the shock velocity sometimes referred to as D and other times referred to as US. The US represents that where the shock velocity has a reference with respect to the material head, which could be moving. The large number of experiments that I mentioned in early 50s and 60s also threw up another very interesting empirical relationship between shock velocity and the particle velocity. And that is a linear relation. D is equal to constant plus S into U. That S parameter, it's called often S parameter. There have been large number of investigation what governs S parameter. But one of the feature which comes out is that if nothing happens to a material, this linear relationship is maintained. For example, if a phase transformation does not take place, or if the material retains the same phase, then it will be a linear relationship. However, if the electronic structure or crystallographic structure changes, this linear relationship will break down. So these kind of relationships have also been used to identify whether for shock compression material is undergoing some fundamental changes. let's once more recapitulate the meanings of the variables in those equations. As I mentioned, dV is the shock velocity with respect to the material head. For a material at rest, D is same as that in the laboratory frame. And in case a material head has another shock, then the shock velocity in the laboratory and the material reference and the material frame of reference would be different. There is a term called shock impedance. It is rho naught into D or rho into D. It's a very very useful parameter which characterizes a material, and we will see shortly as to why it is important. So remember that when we talk about shock impedance, one refers to density into shock velocity. And it's partly because the pressure and the particle velocity, they are continuous across an interface. So you can see the impedance kinds of tends to get matched at the interface. So using some of these things, one can obtain certain other observables. We'll see how. In practice, a planar shock front, I discussed it last time, are not infinite laterally. That as we presumed in the first lecture, that in the YZ plane, it's infinite dimensions. But in practice, we know it is not infinite because uniformity of shock compressed region has edges. It has finite dimensions. In principle, the internal energy of the shock compression can be transported out of the shock compressed material. Okay? Because when the information that has edges reaches, so then whatever is really under shock compression can be altered. Consequently, the pressure release waves can propagate into the shock compressed region. Both these phenomena have the potential of changing the conditions in the sample from those of Rankine-Hugomel. This also implies that in case one is doing shock experiments, it has to be designed in a manner that all measurements are complete before the edge waves arrive. Otherwise, data cannot be analyzed in terms of the jump condition. A word about what exactly is a particle velocity. It's a concept which is very specific to the shock waves, because if you view sound waves, the sound waves as they travel into material, it doesn't move the material. They are the oscillations in the local. So velocity of the mass is almost vanishingly small. But view now that suppose view a linear string of atoms connected by springs. If one limit of the spring has infinite rigidity. So then the moment one hits the first atom, the last atom in the string also moves because it has infinite rigidity. So it's instantly moves. Now that's equivalent to saying that the shock velocity is infinite in this particular case. And the other example is, suppose it has no rigidity. Then in that case, shock will only move if the first atom makes an impact with the second atom, and the second makes the third, and so on and so forth. Then only difference between the shock velocity and the particle velocity would be the diameter of the atom. So the shock velocity will move the distance plus the diameter divided by time, while the particle velocity will be the movement of the center of the particle over that period of time. So these two extreme conditions show that shock velocity is either greater or equal to UP, and for most materials, it's greater than UP. You can also view, picturize what exactly UP means. Suppose a person is floating towards the edge of lake in a calm water, a peaceful water, and at some distance, not very far off, a fast motorboat passes. So as the motorboat passes, it generates a wave, which eventually moves to the person uh, who's floating. Uh, then first thing it undergoes that wave, it moves up and down as the wave goes past and hits Earth. Uh, but after a while, the center of mass of the person who was floating also moves towards the Earth. So that lateral that subsequent movement, the later movement, is what the particle velocity is, UP is. So this is important to remember that the particle velocity, the mass velocity gained as a consequence of material being subjected to shock wave. I should also mention that energy has components. We mentioned energy in a very general term, but energy has components uh, which are due to compression, uh, also thermal effects, and so on, because it has all the aspects which contribute to all the variables which contribute to the energy. Once the jump conditions are known, one can try to understand the shock response of a material. But before we go into that, let me mention a couple of other very useful concepts. In an isotherm, we talked about PV states. As the material gets subjected, you can slowly increase pressure and you can move around a curve which represents the pressure and volume states of the material. Unfortunately, it cannot be done so under shocks. A shock wave, to begin with, is in a state which we call as zero. When a material is subjected to a shock wave, it goes to a particular state, say P prime. If you do another experiment with a higher pressure, it goes to P double prime. So one can generate a locus of points by doing numerous experiments of P on the PV plane. So each of that is an experiment. This curve so generated is called Rankine-Hugoniot curve, or commonly Hugoniot curve. And if the initial state is that of ambient conditions, then this curve called principal Hugoniot. Otherwise, it's a general Hugoniot. Suppose you start with a different volume V1 or different density V1, and again do experiments, you will not get the same curve, you will get a different curve. So each Hugoniot is a locus of endpoints in shock loading, and it is specific to a given initial state. This path, which I mentioned, going from here to here or here to there, is called Rayleigh line, and actually that is the mechanical path it takes. It's mechanical states go along this path, moving from this to this. Okay. They don't traverse along this. See, on isotherm, we can this covers the kind of history of the states a material occupies, but not on the shockwave experiments. So the shockwave experiments, the mechanical states move from this to this, while this curve represents the results of numerous experiments. Each experiment, which is essentially destructive in nature, generates only one particular point. It's very expensive to generate a Rankine-Hugoniot curve of an unknown material. So a huge number of experiments have to be done, and this has to be done collaterally. So I mentioned that each dot in this is a result of one experiment consistent with the jump conditions. And Hugoniot is not a PV, it's not a path of PV states take as in an isotherm. The slope of this, which is called Rayleigh line, is related to shock velocity. In fact, using those three jump conditions, you can drive it yourself. That shock speed can be put like this. That is the square root of V naught into this I call Hookean state pH, and V naught divided by V naught minus VH. So if the slope of it is related to the slope of this curve, then the shock velocity is related to the slope of this curve, or the slope of mechanical states, the path of the mechanical states, the path that it connects from initial to the final state. So now you see that rho naught d has what significance. A few more words about the Hookean equation, Hookean and its relationship to the isotherms. Isotherm is this is a compression curve of an isotherm. It's always lying lower than that of Hookean. So this is a Hookean, this is an isotherm. This hashed region is a difference, and mostly the differences in terms of the heat energy, or otherwise the defects energy which goes into the defects or anything else which alters the shock state. So this is the one when one says starting from a calculated or a cold compression curve or an isotherm, one is trying to deduce a Hookean, then one is trying to estimate what are the contributions which contribute to these differences. So this ODABO kind of curve, that is what which contributes to the difference between these two states. Infinity OBC is the cold work which is done under the isothermal compression, and OB and OAD, this part is the based heat on shock loading. Yeah, that's a heat which gets thrown out. Now, given an equation of state of a material, Hookean can be calculated. The converse may not be so. That is, if you know the Hookean, that is a PV states as a consequence of large number of shock states. It's not a unique. There is no unique methodology available which can determine EP as a function of volume. But if you know energy as a function of pressure and volume, then the Hookean can be calculated. Please remember, mentioned here, the energy has to set along the Hookean curve, it has to satisfy this condition. Okay? So specifically, if you want to find out the Hookean states from a given EPV, make sure that it satisfies this particular equation. So I've given an example here. Suppose you have an energy in this functional form, which is pressure plus some parameter, call it the bulk modulus, say, into volume, divided by gamma, which is often called Bruneisan parameter. Some of the subsequent talks will discuss about what Bruneisan parameter represents. Suppose this is the equation of state which is known of a material. We know the K, we know the gamma. So then we write down that this is the equation of state. Then E naught, that is at before the shock, the reaches of compressors, the material, E naught is P naught plus K divided by gamma to V naught. And using jump conditions, one can write down E1 minus E naught is equal to this. Using the third jump condition, one can write down this. So then E1 can be, you can substitute here, V1 plus K gamma into V1 minus V naught, which we have written here, V naught plus K into V naught is equal to this. And if we define strain is equal to 1 minus V1 V0, or it is rho by rho 1, 1 minus rho by rho 1, then V1 can be written in the form, can be solved, and do that algebra, and you will get V1 in terms of these observables. So for P naught is equal to 0, it takes a very simple form. That is the strain multiplied by bulk modulus 1 minus 1 plus gamma by 2. So I showed that in case you know the equation of state, you can deduce the pressure volume states for shock compressed material. That means that for a known energy functional, one can deduce the Hoover curve. Incidentally, this equation, which is mentioned here, is not general enough. It has singularities. You can check it out that if gamma is equal to 2, at V by V naught is equal to half, then the P diverges. And likewise, if gamma is equal to 6, or V by V naught is equal to 3 by 4, P diverges. Okay. Uh, of course, in the real equation of state substitution, what here rise. But if you are, this was a typical example to show that if equation of state is known, you can deduce the Lyapunov curve. And I mentioned that the converse is not true. Let me also ask a question. Does a single shock wave compression have a limiting value? Can it compress to infinitesimally small volume? Does it have any limit, or you can keep compressing? So let us try to deduce what happens in the limiting compression. So mentioned that the shock velocity has a linear relationship of C plus S into UP. For a Higoniu, one can reach a limiting compression if this C is much, much smaller. As you keep on going to higher and higher stresses, this term becomes very large. So when this is very, very small, that is a kind of a limiting compression. Then using the jump condition, one can write down rho 1 by rho naught. I think this was second jump condition, first jump condition. Rho 1 by rho naught equal to d minus u1. Now that can be put in terms of S parameter, just divided by S minus 1. Limiting value of S for a diatomic gas is known to be 5 by 3. So if you put a value of 5 by 3 into this, you see for a diatomic case, the limiting compression is 4. And for a monatomic solid, S parameter has been determined to be in the range of 1.17. If you put this, then the limiting compression becomes 7. So that means for a diatomic gaseous material, the maximum compression you can subject it to for that, materials like hydrogen, nitrogen, oxygen, all these would not go beyond a compression of 4, while monatomic solids can be compressed 7-fold. Can one go higher? We will discuss shortly. But why in a single compression you can't go higher is because if you look into the Hoover curve, it keeps on steepening up as you go to higher and higher compression. It keeps on steepening up. It steepens up basically because as you go to higher and higher compression, larger and larger amount of energy, internal energy, gets pumped into the thermal energy. It doesn't go into the compression. Instead, it goes into the thermal energy. Now let us also look into what happens to the release wave. In the last lecture, we discussed that if you have a release wave, then as it traverses in the material, it becomes more spread out. Now, a release wave can be put into This wave itself cannot be analyzed in terms of the jump conditions, but we can convert into approximations of each of that as a small discontinuous jump and then apply jump conditions. So remember the second jump condition said V1 is equal to rho naught U1 into D. So one can put it in this form, is equal to V1 divided by rho naught U. And so using jump conditions 1, you can see rho naught D is equal to V1 divided by U1. And you can substitute for this, this value using this equation. And so it becomes P1 to rho naught minus U1 minus U1. So P1 minus V1 divided by rho 1 is equal to P1 by P naught minus U1. So you can deduce from here the particle velocity in terms of 1 and the volume. Okay? So U1 square is equal to P1 V0 minus P1. You can use this equation. Let's see what happens. So you can call, therefore, small each of that delta U in each of these jumps is equal to plus minus of delta P, that is P1. P1 is actually with respect to P0. So delta P into small volume change. Okay? So delta V, and because it is a release wave, the V volume is increasing. So this delta V is negative. Delta P is also negative because the pressure is increasing. Incidentally, the plus term means that release wave is moving forward, and that's a notation which is commonly used in shockwave physics. Plus means it's moving forward and minus means it is moving backward. So knowing volume, that means density, and as a function of pressure, the equation can be then generated to how this whole changes, the particle velocity changes. I worked it out here. The release wave is treated as isentropic for equation of state, for which the equation of state is P. V is a function of S. One can write down sound speed C squared is equal to derivative of pressure with respect to density, which can be put like this. And then delta V is equal to minus V squared delta P by C squared. So you can calculate delta U is equal to delta P divided by rho naught C. So one can therefore deduce U minus U naught is equal to this integral, dP rho C. So if one knows volume as a function of pressure, one can integrate this and one can deduce how the release wave evolved. Mentioned the jump conditions in the form of high variables earlier. One can recast some of those things in different forms. One can also write down in the PV plane can then be transformed into PU plane, and one can write down. I just showed this example how the particle velocity can be written in terms of pressure and volume. So U square is Ph minus P naught S. So one can therefore pressure volume curve can then be converted into pressure particle velocity curve. And we will discuss, in some of our later talks, the relevance of this curve. So Hokunyo, as one talks about, could either be represented in the PV plane or it can be represented in the PU plane. So either when you use that Hokunyo of this material is this, one can refer to either of those. The reported curves may refer to either of these two planes. We will see that how it is this PU curve is used to design experiments. In fact, it is more widely used than the PV curve for designing experiments. So this PU curve represents into which the shock is going on the right hand side, forward, generally called forward moving wave. And if it was plotted along the negative direction, you would say backward going wave or left going. Let's quickly see a case where we had an initial material which was unshocked, then it got shocked by the first shock, and then second shock arrived. How the various variables get connected. You can apply jump conditions between this and this, and then you can apply jump conditions. So using conservation law similar to earlier, one can write on this particular state, state 2, in terms of shock velocity across this interface and the particle velocity prior to this. In a very similar manner that we wrote at the jump conditions, the densities and the particle velocities can be related jump condition 1, and the pressures are related like this, and the energies are related like this. So the slope of a Rayleigh line from P1 V1 to V2 is proportional to the distance, or the proportional to the distance is proportional to U2, which is the shock velocity, the second interface, minus U1, which is the particle velocity. Here, scale. Something similar to D minus 2 scalar here. So shock speed is determined by, as I stated earlier, by the slope of the Rayleigh line. I mentioned here P2 minus P1 divided by the volume difference is related to the shock velocity and particle velocity differences. Incidentally, this is a bad example of showing the Higgs curve, and it never happens like this when two shock waves arrive. One is this, and this almost implies as a universal. Now, if this was the initial state, it can go to this state, there's no problem. But for this material, for a state which is this, if you shock, it will not necessarily move on the first initial state. Typically, it is like this. There is an example of double shockwave experiments done on helium. So you have an initial state which you subject, it goes to this. This is the principal Hugoniot, as we call it. Then at some stage you subject it to a second shock, then it is. You see another interesting aspect of this. We talked about, see, this is, for example, helium is monatomic. So in a monatomic, we could have a single shock, we could have been compressed sevenfold at best. Okay. But when you are having first shock and then followed by second shock, then you can go to much smaller volume. You can go to much higher value of compression. Also note, you cannot, if a Hugoniot is of this kind, principal Hugoniot of this kind, which can happen, we will take a solution. You cannot reach this state from here. States are inaccessible because there is a cusp here. You can't just jump. So it has to come here and then there. Multiple multi-shock experiments help achieve higher compression than single wave. As I mentioned, suppose you have a cusp in PV curve, then some regions cannot be reached by single shock. We discussed about the wave stability earlier too, but in terms of the Hugoniot curve, it can be cast in a very simple manner, that the slope of this at 0 compared to the Rayleigh line actually decides whether the material can be shocked or not. Rayleigh line slope has to be higher than this particular tangent slope. Okay? So this implies that this curve has to be concave upwards. If this is not concave upwards, then a large amplitude wave, as it is launched into material, will not shock up. It will actually generate a ramp wave. And there are examples. For example, if you silica in some region, it doesn't show this compression curve, which is concave upwards, then it is used to generate not the shock waves, but ramp waves. I guess I think I will stop here. We will continue discussing how the shock waves now interact. So one object comes flying and makes an impact on this, or two shock waves meet, what happens, how the material states change. Now that we have the basic formalism, that is the jump conditions, we can play around and try to deduce certain insights into the material phenomena as they are subjected to the shocks. We will continue next Tuesday from wave interactions and consequences of the shock states. Thank you very much. If there are any questions for today's talk, I'll be happy to answer.
Sir, it seems like no question on WebEx
So we will
as
stop here.
as well
Sorry.
as
So no questions, right?
no.
So were there any questions about the last talk subsequently sent?
checks.
Or otherwise, if some questions come, you can forward it to me by email. I can
Yes, yes.
check it later.
Okay.
And also, Rishabh, I noted while making presentation that there are a few probably spelling mistakes here and there. I can probably correct that and send it back to you this